I heard these are like relaxed. Yeah. What kind of pie?
That'll make it easier for Jefferson to stay awake. Okay. Yeah. Or at least easier for me to ignore it. What? No, I can't control them. That's fine. I was that close to the Okay, I'll turn on the light. I don't care. I just thought it was a little better to see. This is so animal.
I want to double in.
Oh yeah, that's
I agree.
Since the time when you first you can turn them off.
I can't control them that way. Here, let me show you what I have. Yeah, these two are just stupid.
Oh, that's pretty nice.
Turn off those two lights.
Yeah. Yeah, I know. And I've been trying to get them to wire it so that I could just shut off these.
Yeah. I think they would just do that. You get a wire to just good pattern.
Maybe.
Well, yeah, we could do that. Okay, you guys. I had planned to carve out probably 20 or 30 minutes just to do problems from the previous section. So if you're even sort of on the border about whether you wanted to ask a question about homework, please feel free. And I'll just cut us off maybe at, well, that clock is wrong, but does that say noon?
Yeah.
It's been an hour behind the whole.
Okay.
No way. I never noticed that.
Today's lesson is essentially, the new material today is center of mass. You probably did center of mass in Calc 2 in the one-dimensional case, where essentially in the one-dimensional case it's really just a matter of trying to find the place where some object balances, the point where it balances. And for a uniform piece of whatever, like a piece of chalk, that thing's going to balance right in the middle. But if you have some sort of weirder object that's like heavy on this side and light on this side, then what happens is the center of mass sort of moves towards the heavy side. What we want to do is take that same idea and generalize it. Can we find a balance point for a two-dimensional piece of something or other? And not only with uniform density, but where maybe one side is heavier than the other, or so, or what have you. It's just a straightforward application of double integration, and I think we can probably go through the actual setup in probably 10 minutes and maybe do a couple of examples. So, with that said, are there questions on the web work? Let's focus on section 15.2, but I would also entertain questions from 15.1 after we get through the polar stuff. So, Chloe? Okay. So number 3, let me see if I can blow this up a little bit. What is the blow up thing? Is it like Control Shift Plus or something? Yeah. There we go. It's a little better anyway. Okay. I guess the first thing to really check here is, do you see why this is an ice cream cone shaped thing? Maybe. Okay. So let's focus on z equals the square root of x squared plus y squared. And this is a cone. It's the upper part of a 45-degree angle cone. How do you see that? How do you see that? I think the easiest way to see it is the height above the XY plane is exactly the same as what? The distance from the origin. So if you go out a distance from the origin, this distance is the same as this distance. And then there's no theta dependence. It's just, it's just z equals that, and so it's circularly symmetric, and it's this upper part of a cone. Okay, let's look at the other one. Oops, 32, not 3 squared. This guy, again, we've got to get familiar with some of these common equations of curves and surfaces. Does anybody recognize what this is? What surface this describes? It's the sphere, almost. It's the upper half of a sphere, right? It's the northern hemisphere. How do you see that? Let's square both sides. And then take these guys and send them to the other side. S 32 or 36? I don't even remember now. 32. Okay. So this is a sphere of radius root 32. So you've got this cone that goes off for infinity, and then you've got this sphere of radius root 32. Like that. And what's going to happen is the cone is going to go up and it's going to pick off a piece of the sphere. And how are those two surfaces going to intersect with each other? In a circle that's parallel to the XY plane, how do you find out what that circle is? Yeah, remember what I said, you can't generally do this, but in the case where you can solve for z, z equals f of xy, z equals g of xy, it's okay to set f and g equal to each other and solve for x and y, and what you're going to find is the shape in the xy plane inside of which, or where these guys intersect. So let's do that. Let's take these two guys and set them equal to each other. That's the square root of x squared plus y squared equals the square root of 32 minus x squared minus y squared. Not super helpful yet. Let's square both sides. Oh, come on. Move the x squareds and the y squareds to one side. Divide by 2. Now how do I interpret this? X squared plus y squared equals 16. I already know the simple answer. It's a circle of radius 4. What is the meaning of the circle of radius 4 in this context? What is it telling me?
That's the area of which you
Okay, so you know me. I like to walk around in the XY plane. So I'm walking around in the XY plane, and I'm inside the circle of radius 4. What's happening above me? Why is this circle important to me above? Above this circle is where everything is happening. Above this circle is where the ice cream cone is. So if I stood right in the middle, how could I describe my situation? Where would I be in the ice cream cone? I'd be sticky. I'd be at the bottom, and that's like I like to bite the bottom off, and you know. I'd be right at the bottom, right at the point of the cone. Above me is the ice cream and the ball of ice cream at the top. Okay. Now, How do I compute the volume of that figure? I compute the volume underneath the dome, and I subtract the volume underneath the cone, right? It's the volume underneath the dome minus the volume underneath the cone. And that gives me the volume inside. So what's the integrand look like? What's the thing that I'm integrating? Not the limits of integration, but the thing inside the integral. What am I trying to what do I integrate?
Well, don't you have to convert it to polar coordinates first?
We can do that now or we can do it later. Let's do it later.
Can you say the volume thing again? You take the dome and you subtract the area underneath the cone?
Yes, so I've got all this stuff underneath the dome, right? And then I've got this stuff underneath the cone. So I take the stuff under the dome minus the stuff under the cone, and what I get is the stuff inside the ice cream cone. The way to do that is to take the top surface, the equation of the top surface, which is the square root of 32 minus x squared minus y squared, and subtract the equation of the bottom surface, which is the square root of x squared plus y squared. Just dump that into the integrand, and you're ready to go. Okay, so as Tate mentioned, we're supposed to do this in polar, so let's convert both of these to polar. So how does the cone look in polar coordinates? Z equals r, and that's pretty easy to see because, in fact, r is just the distance from the origin, which is precisely the square root of x squared plus y squared. So you can just replace that with r. How about this next guy down here? How do we do this in polar? It's the square root of 32 minus r squared, but what if you're not so sure, not so savvy that you can pick that out? What's a rock solid way to get you to the polar version? Let x equal r cosine theta, let y equal r sine theta. So let's do that in our heads here. X is r cosine theta, y is r sine theta. R squared cosine squared theta plus r squared sine squared theta. Factor out the r squared. What's left behind? Cosine squared plus sine squared, which is 1. That whole thing just turns into minus, there's a minus sign there. That whole thing just turns into minus r squared. So this guy is 32 minus r squared. I realize these notes are a massive confusion, but you guys have worked on this problem presumably, so I'm just kind of giving you hints along the way. Okay, so we've got the region of integration. We've got the top surface minus the bottom surface. How does this integral finish? R d theta. Yes, do not forget that r. In fact, without that r, this integral is much harder. Well, without that r, it's wrong. So let's get that out of the way right off the bat. But it's often the case that this r actually saves you. It introduces a piece that's necessary to do a u substitution and make the integral fairly easy. Okay, the region. How do we describe that region in polar coordinates? R goes from 0 to 4. And theta is the entire circle, 0 to 2 pi. Yes. I'll leave that integral to your able and capable hands. Mostly because I don't feel like doing it. Next question.
I have a hard time always determining what the limit should be. I'm just on any problem in general.
Yeah.
What's a good way to look at that?
Each problem individually.
Okay.
Grind your way through it. And then hopefully the next one is a little bit easier. I can give you a couple of tips. For example, when you're trying to, if you're given an integral, like let's go to the book here. I could be using the mouse here. Okay. for these guys down here, if you're given an integral, it's pretty straightforward to find the region, right? Because you look at what's the first variable you're integrating with respect to? It's y. So this is just y equals 0 up to y equals the square root of 9 minus x squared.
So get it more like, because the polar one was already given, but probably even like in more general terms, like the last one. It's like just determining the limits.
Yeah, I think what you need to think about, like for the ice cream cone one, is what you want to think about is little areas in the xy plane times heights. And that's what you want to try to build and represent. So what I did in that other problem was, right, the little areas are down here, right, and they're described by this thing, right? So I'm taking little areas times heights to get volumes. And the height, which is described by this thing, sorry, let me be a little more precise here. Right, that's just at a particular location. It's from here to here. Okay, so I've got this distance, this height, this column, and then below it there's this little piece of area. And that little piece of area times that height gives me, roughly speaking, the volume of the column. And then the integral adds up all those columns around. That's the picture that goes through my head all the time. I know that I've got to somehow describe the base of the columns, and then I've got to describe the heights of the columns. And that's what guides me. Other questions? Chat.
Can you just do like number 2 in the text?
2 in the text from section 15.2? Find the volume inside both r equals 1 and r squared plus z squared equals 4. Okay, what does, let's see here. What is r equals 1?
Circle radius.
It's a circle of radius 1, but in the context of cylindrical coordinates, it's a cylinder radius 1, centered at the origin. Okay, good. What about this other one, this z squared equals 4 minus r squared? Why? I heard it out there somewhere.
It's a sphere.
Yeah, but why?
And you make r squared, x squared plus y squared.
Yeah, r squared is x squared plus y squared, and so the left-hand side becomes x squared plus y squared plus z squared, which is something we're familiar with. So it's fine, Claire, if you just recognize that as a sphere. I didn't mean to jump on you. But if you're a little bit like, really, r squared plus z squared is a sphere, try to turn it into something that will convince you that it's a sphere. And the way to do that is r squared is equal to x squared plus y squared. Does everybody know that? And you put that in there, and now you've got a sphere. And what's the radius of the sphere? 2. Okay. So I don't think it's totally necessary to build, to sketch a figure every time. In fact, what I'd like to see you guys do, at least for fairly straightforward examples, is to not really worry about what it actually looks like, other than just sort of in generic terms. So I've got this sphere of radius 2, and I've got this cylinder of radius 1 going up through the middle. Can you visualize that kind of? Okay. Where are the bases of all the columns living? If I'm trying to find that volume, and where is the volume? Okay, so it's inside, so it actually goes from the top of the sphere to the bottom of the sphere. It's like the core of the sphere, like an apple core or something. So where do the bases of these little columns live, or where in the xy plane? Right, the circle of radius 1, all inside there. So that's the region of integration. And how tall is one of the columns? Well, it depends on where you are, right? Depends on where you are. How do you describe, what's a formula for how tall one of the columns is?
For the z component, for making z equal for the circle.
Right, so I'll try to sketch this poorly, and, well, I won't try to sketch it poorly, but I will sketch it poorly. Okay, so there's kind of the volume that we're talking about. The XY plane is kind of, ooh, that was bad. Okay, the XY plane is kind of right in here. Okay. So we have r squared plus z squared equals 4, aka z squared equals 4 minus r squared. Z is equal to plus or minus the square root of 4 minus r squared. Does everybody buy that? Okay, the region of integration in polar coordinates. R goes from what to what? 0 to 1. Theta goes from 0 to 2 pi. How tall is one of these columns? Say the one that starts here and goes down to here.
Is it 2 times the square root of 1 minus r squared?
It's the top surface, which is what? Square root of 4 minus r squared, minus the bottom surface, which is minus the square root of 4 minus r squared. Minus a minus is plus. That gives me 2 of those guys. And how do I finish? RD theta. And again, that's not a terrible integral because a u substitution will work really well here.
Can you go over how you found the integrand again?
So the integrand, the plus is the top, and the minus is the bottom. Okay, so the plus describes this part, and the minus describes this part. So if I want to know how long or how tall this column is, I take the top minus the bottom, and that gives me 2 square root 4 minus r squared. Is that a little better, Jade? Okay, next question, or still for this one?
Yeah.
Go ahead.
Is this inner circle the r equals 1?
Yes, it's
Oh.
this. That whole inner thing is the cylinder r equals 1. Yeah.
So we're not treating this as though volume cancels when it's above or below the x, y plane? Because in that case, wouldn't the volume be 0?
Right. We're that's a sort of a subtle point, but if you have a surface, right, that sometimes it's above the xy plane and sometimes it's below, and you integrate in a region where it's above and then goes below, you're going to get cancellation there. That's a little different than what's going on here. What's going on here is I'm simply, in a way, I guess it's the same, right? I'm taking the top surface minus the bottom surface. The bottom surface, in terms of volume, is going to be what? If I ignored the top half of this thing and I just computed this volume using this bottom surface, I would get a negative volume. So in a way, the same thing's happening. I'm taking the top volume, which is positive, minus the bottom volume, which is negative, and they actually add together. Other questions? We can move on if you'd like. Okay. Time for at least one more. Heather.
Number 7 on the work. It's got your hint that you sent out, but I just had a hard time sending out.
That was a harder problem. I don't. Oh, maybe this isn't the one I'm thinking of.
Number 5 will go over r squared.
5 was rough.
Okay, so use polar coordinates to evaluate the integral, which gives the area which lies in the first quadrant between these two circles. You have to sketch the two circles first of all. This one I'm sure that you could handle.
Yeah.
This one you may have been a little bit perplexed by. How do you figure out what circle this represents? You have to complete the square, which is something that we did at the beginning of the semester. You have to rewrite this as x minus 10 squared plus y squared. And then when you do that, complete the square, you're going to introduce a 100 that goes over to the other side. Does that ring a bell? So what you find, and I'll let you do the work, but what you'll find is a circle that's centered at 10, 0 of radius 10. If you complete the square on that and move it over to the right-hand side. Does everybody think they can do that? I'm happy to do it. This is a circle of radius 20. So the picture see if I can get it right here. There's a circle of radius 10. Boy, that's terrible. I can't write on it this way. No, dang it. Okay, last chance. Then I walk away. There we go. There's a circle of radius 10. And the circle of radius 20, centered at the origin, kind of starts here. Let me tick off some points here, 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 and here. Okay, so let's go back and remind ourselves what we had. We had the circle of radius 20 centered at the origin. We have the circle of radius 10 centered at 10, 0. So this problem is sort of specifically designed no matter what your numbers are, you're going to get a figure that looks like that. What area were we interested in? We were interested in the first quadrant. Let me go back. And which gives the area. This is not something that I talked about explicitly, but it's something that the book talks about. If you want to compute the area of a region, you compute this integral. No integrand, just 1 as the integrand. Okay? So if I want to compute the area of the red region, all I really have to do is figure out how to describe it in polar coordinates. And describing this guy in polar coordinates is not so bad. R always goes from this curve to this curve. So for example, the upper limit in R, in my problem is going to be 20.
Show that again.
Yeah, so this is a weird shape to think about, but remember that we want to build the region out of rays. So a ray from here to here is going to start here and end here. A ray from here along here is going to start here and end here. And it's even harder to see, but a ray right here is going to start here and end here. So even though it may not look like it intuitively, the rays, the R values always start here and end here. Start here, end here, start here, end here. The end point is easy. R is equal to 20. The starting point, a little less easy. How are we going to do that one? Joe?
It's really pi over 2 if you don't go in the first quadrant. It's still 2 pi.
I'm sorry, it should be pi over 2, yes. Yeah, pi over 2 describes the first quadrant. Exactly. Clayton, do you have an idea about that?
Well, it's starting at the top half of the circle. It only starts at the top half of the circle, so you can do the square root of 10 minus r.
Yeah, so essentially what you've got to do, you've got to convert this thing to polar coordinates. The second equation, you've got to convert it to polar coordinates and solve for r. How do you convert this to polar coordinates? Jefferson.
R squared minus 20 times
R cosine theta. So yeah, if I drop in R cosine theta here and R sine theta here, these two guys are going to combine and give me a what? and r squared. I don't get any niceness with this. I just am stuck with the r cosine theta here. So I have r squared minus 20r cosine theta.
Why can't you just do this problem like there is grade 5?
Because you were supposed to use an integral to do it. I think it even says. It says using polar coordinates, evaluate the integral, which gives the area which lies in the first quadrant. Because you've already had 5th grade math, and so now we're doing calculus. One of the reasons that we like to do problems like this in calculus is to, and I'm not sure how valuable this is, although clearly I think it's got some value because I computed the volume of the sphere on Wednesday, remember that? It's really just to drive home the point that this is not magic, that these things really are producing known geometric quantities. So when I computed the volume of the sphere last time, I showed you that the integral, the volume integral, is actually consistent with known geometric formulas. What Jefferson is talking about here is this is not a difficult area to compute, even if you're in 5th grade, right? It's just a quarter of the area of this circle minus half the area of that circle, and you're done. And an interesting above and beyond, if this were an above and beyond problem, would be maybe to pull that up and show it to me. But if on an exam or something like that, I say use the integral to do x, y, or z, you better use the integral to do that. Okay? Okay. Okay, so I'm gonna, where are we here? We've got, we've converted this thing. Let me factor out an r. And it turns out that we don't care about this part, and what we really have is r is equal to 20 cosine theta. So the upper or the lower limit is going to be 20 cosine theta, 1 r d theta.
So why don't we care about the r squared? Can we divide it on both sides?
Either r is equal to 0 or r is equal to this other thing. R equals 0 is a point at the origin, which is clearly not the curve that we're interested in. So it must be the other one. That's the easiest argument. One more. 5? Web work 5? Yeah, I threw 5 in there mostly because I thought it was cute, but often the things that I think are cute are not the things that you guys think are cute. And I think that was the case here. This integral comes up quite a lot, especially in statistics. Any of you guys in stats this semester? Have you seen that one at all? No?
Is that normal?
You haven't done any integration? Yeah, exactly. It's the normal. This is essentially a normal curve. It's a bell curve. And so I don't know that it's normalized. I think you have to, I don't remember what it works out to be. Yeah. So, but what you can do is put a constant in front of this and turn it into a Gaussian distribution. And so this is a hard integral to do. Let's forget about this and just look at this. Can you do this integral? No, because there's no du, right? You'd like to sort of let u equal x squared, but then du is 2x dx, and you're stuck. Is there any other way to do it? No, but it turns out that if you use some of the stuff that we've learned in Calc 2, or sorry, Calc 3 here, we can compute this integral and observe that this integral is actually the square of this integral, and take the square root, and you're done. And that's what I tried to get at with the notes that I sent around in the maybe yesterday. I don't know if you had a chance to read that, but let me just walk you through. First of all, what's r squared? Those of you that read the email. It's the entire plane. The entire xy plane is r2 or r squared. How do you describe the entire plane in polar coordinates?
From 0 to infinity and theta from 0 to
Right. So if I let r go from 0 to infinity, and then I take all possible angles, I'm going to cover the whole plane, right? Okay. So the region, the limits of integration for the entire plane in polar coordinates, 0 to infinity, 0 to 2 pi. Does everybody buy that? Okay. What does x squared plus y squared turn into in polar coordinates? R squared. Not so bad. And what does this turn into? R d theta. And now we have a du. So you've got an r squared up there and a du. And you can do the integral. It's an improper integral. Do you remember how to do improper integrals? Technically, what you're supposed to do is replace the infinity with some letter L or M or something like that. Compute the integral and then let L go to infinity. Now, does it slightly ring a bell? 9 times out of 10, once you get past that introduction to improper integrals, you kind of do that in your head. Okay. So it is an improper integral. And then the other thing to note was the thing from the notes. And I don't know if I can pull that up here easily. Let me see if I can. Can't remember what I called it. There we go. So I gave you this theorem that said if your integrand can be written as the product of a function solely of x and a product of a function solely of y, then you can actually take this integral and separate it into 2 regular integrals like this. And then I actually proved it for you. How is that relevant to the problem at hand? Whoops. This is actually a separable integrand. E to the minus x squared minus y squared is actually e to the minus x squared times e to the minus y squared, right? So now I can take that and separate it out. And then when I separate it out, I'm left with 2 integrals like this multiplied together. So this is really just the square of this. So once I calculate this, I take its square root and I get that. I'm not sure how valuable this particular problem is to the overall understanding of polar integration in 2 dimensions, but there you have it. It's a fun problem, for me anyway. Logan.
I just have a quick question. I think it's on 4.
4.
So your xy is equal to xy. So how do you rewrite that? Is that just r cosine theta, r sine theta?
Yep.
How do you rewrite that? Okay.
R squared, sorry. And in fact, it'll be r cubed cosine theta, sine theta, because you'll get an extra r from the r d theta. Yes?
Okay.
Okay, I think that's all we have time for. If I have time at the end, after I do center of mass, I may entertain another question or two. Okay. Center of mass in 2D. You may recall from Calc 1, you probably don't, but you might recall from Calc 1 that the center of mass of some variably dense bar of metal, say.
What's the symbol above the X?
That's a bar. It's just a line. Okay, so you might recall from Calc 1 that, Calc 2, that the center of mass of some thin rod is given by this formula. So it's the integral from a to b x times sigma x dx over the integral from a to b of sigma x dx. What's going on here? You have this bar, and you've got the origin. And what you're really trying to do is figure out where the balance point is. And you'll remember, let's pretend that, you know, somebody's finger is right here underneath the origin. Right, so my finger is right here underneath the origin. And let's pretend that gravity is acting down like this. So if it's really heavy over here, the thing's going to tilt this way. And if it's really heavy over here, it's going to tilt this way. But it's a little more complicated than that. Like a 1 kilogram mass that's sitting right here is going to have much less effect than a 1 kilogram mass sitting out here, right? Okay, so the distance that the mass is from the origin is going to have an effect here. And that's where this comes from. So we look at a little infinitesimal piece of the rod, and we ask ourselves, how much does that weigh? Well, it weighs sigma x dx. And how much is it going to contribute to, well, this guy's going to want to push it down, right? It's going to push it so that the whole thing wants to rotate counterclockwise. And how much is that little mass going to contribute? Well, it depends on how far it is from the origin. So we'll throw in an x there. And if you want to figure out sort of the net contribution of all these little infinitesimal pieces of mass, then you integrate. And then the thing at the bottom, in a way, just kind of normalizes the whole process so that you get a valid coordinate. So if you're curious about that, it's in, I think it's in chapter 9 of the text, and you can read about that. The thing we're about here today is, can we find a balance point for a region R? So let's pretend that we've got some region R in the xy plane. Okay, and now gravity acts into the plane. And I want to find the balance point. I'll just kind of eyeball it here. Maybe right there is the balance point. So if I stick my finger underneath and gravity's going into the plane, maybe this shape, whatever it is, this flat piece of whatever metal, maybe it balances right there at x. That's the goal. So instead of gravity acting down like this, now gravity is acting into the board, and we're trying to balance this thing on a fingertip like that. And we want to generalize. We want to allow for the possibility, not that it's just some uniformly dense kind of shape, but rather that it might be really heavy over here and really light over here. In fact, this binder is like that. It's heavy over on this side, and it's really light over on this side, which means the center of mass probably is going to be right in the middle in this direction, maybe right here, but it's going to tend towards the bottom in this direction because it's got all this heavy metal and stuff on this side, right? So we'd like to get a formula for that. And it turns out that the formula for x bar up here generalizes quite nicely. So if we want to find that point in 2 dimensions, we need 2 numbers. We need x bar and y bar. X bar is just the integral over the region x times the density xy dA, and You have to normalize it. And y bar is y times sigma xy dA over sigma xy dA. And this is just, the bottom is just the mass of the shape. Does everybody see that, kind of? If I take the density function, what is a density function? Essentially, it's the mass per unit area of the whole figure. If I take a particular location and I times it by a little piece of area, then what I get is a little piece of mass, and then the integral adds it all up. So this is density times area, which gives me mass. Sum over the entire region gives me the full mass of the region. The top is not just the mass, right? How is the top different from the bottom? It's got this extra y in there, right? And up here it has this extra x in there. What those guys are doing is they're playing the important role of adding in the distance from either the x or the y axis to tell you how much weight, how much downward force the thing is going to contribute. So you need those guys in there. And there's a somewhat confusing notation in the book. That thing in the numerator is called the moment of the figure around the y-axis, and the thing in that mx is the moment of the figure around the x-axis. And what's weird about it is my goes with x bar and mx goes with y bar. Don't worry too much about that. That's just notation. The really important thing is x goes with x, y goes with y. Okay, what you actually call these things is not terribly important. Let me just try to briefly motivate why they have these confusing names. I mean, are we really just trying to mess with you, or is there some purpose to this? And the answer is there is a purpose to this. My. What we're doing here is we're looking at, we've got x in here, so what we care about is x is really a measure of how far you are from the y-axis, right? So if I take this little piece of mass here and I multiply it by x, what I'm really doing is assessing how it wants to, remember gravity is acting into the plane, so that guy, in terms of its contribution to, right, that guy wants to spin this figure around the y-axis, right? Yeah, move this down here. If I press really hard on this right here and pretend that the y-axis is some like metal bar and this guy's balanced on it, if I press really hard on it, that thing's going to go like this, right? That's what this point wants to do. No matter what else is going on around it, this guy wants to push down and push that thing down around the y-axis. That's why it's called my, because it tells you how much it wants to rotate the y-axis. My tells you how much it wants to rotate the y-axis. By contrast, let's look at mx, right, which has the y in it. Now what we're doing is we're measuring this distance. Well, if I push down on this and I've got this horizontal thing and I push down on it, it wants to go that way, and what it's really measuring is how much it wants to rotate the x-axis. So that's why it's called mx. So y tells me, this x integral tells me how much I want to rotate the y-axis, and the y integral tells me how much I want to rotate the x-axis. That's the justification. This is not an engineering school, so you'll likely never see these two quantities again. But if you were to go on to graduate school in engineering, which some of our majors do, some of our math majors do, this kind of stuff gets really important when you start studying mechanics. Okay. Right, we really care about if there's a whole lot of weight over on this side of the building, we care about the moments that weight is placing on the other structural members of the building. We care a lot about that because certain beams only have certain capacities, and you can twist them this way and bend them this way and so forth. So there are all these different moments, and that's where this stuff comes from. So that's a little cultural note from the culture of engineering. Okay, find the center of mass. Find the center of mass of a triangular piece of metal and I should say a flat triangular piece of metal with vertices vertices 0, 0, 1, 0, and 0, 2 with density function sigma x of y is just x plus y. Now you don't need to plot these if you don't want to, but I think for just the sake of illustration, sake of clarity, let's do that here. There's 0, 0. Let's say that this guy 1, 2, 3, 4. Let's say that this is 1, 0. And then 1, 2, 3, 4, 5, 6, 7, 8. That guy up there. All right. So here's the piece of metal. The density function. Okay, where is this guy the lightest? This piece of metal. Why do you say that? Yeah, the density here is you plug in x equals 0 and y equals 0. So in fact, this thing is very light right here. It has no density right here. But as you creep away from this point in either the positive x or the positive y direction, this thing starts to get heavy. Where is this guy heaviest, do you imagine? Probably 2, 0. I don't know. You have to figure it out. 0, 2, excuse me. Yeah, probably 0, 2. Anyway, so that's just qualitatively so that we understand what's going on here. The center of mass is going to be somewhere inside this triangle. And it's probably going to be, relatively speaking, far away from this point because this is really light. And maybe sort of hedging that way and hedging that way. So maybe sort of up in here somewhere. Let's calculate this guy. We need to describe this region. Let's look at my. Okay, so there's the integrand for my. It's x times the density function sigma. Let's pick a direction of integration. I guess we'll just go y first and then x. So we're back to section 1 here. So if I'm going to go in this direction first, oops, sorry. So if I'm going to go in that direction first, parallel to the y-axis, where does y always start? 0. And where does it end up? It ends up on that line. So what do we have to do here? We have to find the equation of the line. What's the slope of that line? 2. So it's 2x. And what's the intercept?
Isn't it, it's shooting
Negative 2, yes. And the intercept? 2. So there's the line. Okay, so the upper limit is negative 2x plus 2. All right, over what range of x values am I building these vertical slices? 0 to 1. And I've done this integral, and it works out to be 1/3.
That's my equals.
That's my. Okay, mx, 0 to 1, 0 to negative 2x plus 2, same integrand, sorry, same density function. Okay, the limits are the same because the region's the same. The density is the same because it's the same density. But remember that mx involves a y here. So you throw that y in there. So these integrals are going to be different. Why are they going to be different? Because this is a y, not an x. And there's no shortcut around this. There's no handy-dandy formula that says if you replace x with y, you get this. You just got to do it all again. If you do it all again, you get 5/6. Now, I've got my and mx. What's left to compute? I need to find m. Same region. And that's x plus y, dy dx. And there's neither an extra x nor an extra y in this problem. It's just integrating the density function. And again, I'd love to tell you there's a simple formula for when you drop the y or drop the x, but there isn't. You just have to do it all again. I've done this one, and it works out to be 1. That's convenient. So with that information in hand, we see that x bar, which is my over m, is just 1/3, and y bar, which is mx over m, is 5/6. That, my claim is, that's the balance point. Well, let's look at it and at least see if it's slightly reasonable. 1/3 and 5/6. 1/3 is probably right here-ish. 5/6. Let's see. This is 1 right here. So 5/6 is, I don't know, ish. It's kind of right there, maybe. I mean, I don't know if it's perfect, but it's kind of in the ballpark of where we would expect it based on this density function.
Why don't the limits of integration change for my and mx?
Because the region didn't change.
They're still going.
Yep, the region didn't change. Okay, let's do one more and then I'll let you go. You can enjoy your weekends. Find the center of mass of the upper half of the circle x squared plus y squared equals a squared with density function sigma of x and y equal to some constant k times the square root of x squared plus y squared. Center of mass, upper half of this circle. Let's just briefly talk about this density function. Where is this thing the lightest? Again with the origin thing. Okay, so it's Lightest at the origin. Where is it heaviest? Around the rim. Around the circular rim. And then, so it's uniformly heavy out here, right? It's going to be Ka heavy out there. And in here, it's variable. As you go back in towards the center, it gets lighter, and then it gets heavier as you go back out. Yeah? Okay. Where would you expect the center of mass, the balance point for this figure? Remember, gravity is acting into the blackboard. And I want to put my finger underneath this thing and balance it. Go ahead.
Well, it'll be on the y-axis.
So why would you think it would be on the y-axis?
Because it's symmetric.
The figure is symmetric, and the density is symmetric. Both of those things have to be symmetric to make that argument, but you're correct. Do you have a comment,
No,
Heather?
just-
Okay, got it. Okay, so everybody's good with that? Now, where would you expect, so the x coordinate, x bar, is going to be 0. Definitely. Y bar? It's hard to judge, right? Because the circle isn't symmetric in any way. You know, maybe here, but then it's also heavier out here than it is down here, or maybe not. I don't know. So that's why you have calculus. All right, so my. Oh,
You don't have to calculate, but you only have to calculate.
what's the best coordinate system here? Yeah, polar. So we want to use polar. Go away. Okay. Use polar coordinates. How do you describe this region in polar coordinates? Yeah, so R is going to go from 0 to A. Theta? 0 to pi, good, because it's just that upper semicircle. My is x times sigma xy dA. What happens to the x? It becomes r cosine theta. What happens to the sigma? Sigma is actually kr. Exactly. Does everybody see that? So sigma is kr. And then r dr d theta. So yes, there really is an r cubed in this problem. And you have to integrate r cubed to kr cubed cosine theta. I'm not going to do this integral, but it's a pretty straightforward integral, right? Where does the 0 come from?
There's a question. Does that still solve for my, or does it solve for m theta?
This is my.
Where'd the KR come from again?
Yeah, it's from the density function up here.
Okay.
So sigma is k times the square root of x squared plus y squared. Let me show you the handy little trick that I sent around the notes for. You can break this integral up like this, because in fact this integrand is separable. You can write this as a product of a function only in r and a product and a function only in theta. So I take the theta integral, pull it out, take the r integral, pull it out. Don't even bother with that one because this is 0. So the whole thing is 0. Mx.
How would you know to do
Yeah.
that?
When do you know if that's appropriate?
When the integrand is separable.
So basically just like when it's all multiplied together, you can just divide it up.
So if the integrand is a function of x times a function of y, then you can separate them. If it's a function of r times a function of theta, you can separate them.
So as long as you can like completely isolate the x's and y's without.
Exactly.
Okay.
Read the notes, the supplemental notes that I sent around in that email. Okay, MX, and Heather had an interesting comment / question here. This really is still MY. Even though I take this thing and I convert it to polar coordinates, it's still going to give me a y coordinate in Cartesian coordinates. It's not giving me some sort of weird polar coordinate because I switched to polar. And that's kind of why I wrote this thing up here first. This is my, and at this point I'm switching to polar coordinates just to compute the integral. So it has no physical meaning at all other than just making the integral easy. MX, same region. R sine theta. K R d theta. Yeah, we have to have Pirate Day in here. I know we're having Pirate Day, aren't we? This is also separable. So the theta can be pulled out and joined with the theta. The r's can be separated out. Now, the big difference here, and it's cool how math works sometimes. This guy's not 0, right? Because when I integrate it, I get cosine, and when you plug in pi and you plug in 0, you're going to get a 2 out of that. This guy, when you integrate it, turns into a sine. When you plug in 0, you get 0. When you plug in pi, you get 0, you get 0. So that's reassuring because we didn't want this thing to be 0, because we know that the balance point is not 0, 0. So I didn't do this integral. I'll let you figure it out. And then there's m. And that's the last integral, and that's the integral from 0 to pi, 0 to a, kr times r d theta. And now the theta integral is easy because it just turns into a pi. And m is just that integral.
So you can even separate out the integral from 0 to pi of d theta.
Right, because that's just secretly a 1.
Right.
Pull it out and do that. Yeah, it's definitely a handy trick. And after I wrote up the notes, I sent them to David so he would put that in the book because it's not in the book right now, and it needs to be there. Okay, so this whole section is really just applying this formula, and when you're doing these problems, please do pay attention to the results and see if the position of the balance point makes sense qualitatively. Have a nice weekend.
I think simple question.
Okay.
Why is it 1 for this is number 7? Why do we just when we're doing a circle is it just 1?
Let me pause my